A correlation regression analysis of paired data should include an investigation of outliers and influential points defined as follows. In a scatter plot, an outlier is a point lying far away from the other data points. Paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line. To determine whether a point is an outlier, examine the scatter plot to see if the point is far away from the others. Here's how to determine if a point is an influential point. First, graph the regression line resulting from the data with the point included. Then graph the regression line resulting from the data with the point excluded. If the regression line changes by a considerable amount, the point is influential. Consider the 23 pairs of chocolate Nobel data from table 10.1. The scatter plot located to the left below shows the regression line. If we include an additional point of data, x equals 50 and y equals 0, we get the regression line to the right below. The additional point, 50, 0, is an influential point because the graph of the regression line did change considerably. Compare the two graphs to see clearly that the addition of this one pair of values has a very dramatic effect on the regression line. So that additional point is an influential point. The additional point is also an outlier because it is far from the other points. The regression equation represents the straight line that best fits the data. The criterion to determine the line that is better than all others is based on the vertical distances between the original data points and the regression line. Such distances are called residuals. For a pair of sample x and y values, the residual is the difference between the observed sample value of y and the y value that is predicted by using the regression equation. That is, residual equals observed y minus predicted y equals y minus y hat. Residuals can be easily understood by examining the graph below, which corresponds to this table. And this table has x values of 8, 12, 20, and 24, with corresponding y values of 4, 24, 8, and 32. The paired data are plotted as red points. Consider the sample point with coordinates 8, 4, which is right here. I don't know if you can see that. Hopefully you can. I'm moving the little pointer around it, but I don't know if that actually shows up on the video. Consider the sample point with coordinates 8, 4. If we substitute x equals 8 into the regression equation, y hat equals 1 plus x, we get a predicted value of y hat equals 9. But for x equals 8, the actual observed sample value is y equals 4. The difference, y minus y hat equals 4 minus 9 equals negative 5, is a residual. The regression equation represents the line that best fits the points according to the following least squares property. A straight line satisfies the least squares property if the sum of the squares of the residuals are the smallest sums possible. From the figure in the previous slide, we see that the residuals are negative 5, 11, negative 13, and 7. So the sum of their squares is negative 5 squared plus 11 squared plus negative 13 squared plus 7 squared equals 364. We can visualize the least squares property by referring to the figure, where the squares of the residuals are represented by the shaded square areas. The sum of the shaded square areas is 364, which is the smallest sum possible. Use any other straight line, and the shaded squares will combine to produce an area larger than the combined shaded area of 364. A residual plot can be a helpful tool for analyzing correlation and regression results and for checking the requirements necessary for making inferences about correlation and regression. A residual plot is a scatter plot of the xy values after each of the y coordinate values has been replaced by the residual value y minus y hat, where y hat denotes the predicted value of y. That is, a residual plot is the plot of the graph of the points x, y minus y hat. To construct a residual plot, draw a horizontal reference line through the residual value of 0, then plot the paired values of x, y minus y hat. Because the manual construction of residual plots can be tedious, the use of technology is strongly recommended. When analyzing a residual plot, look for a pattern in the way the points are configured and use these criteria. The residual plot should not have any obvious pattern, not even a straight line pattern. This lack of a pattern confirms that a scatter plot of the sample data is a straight line pattern instead of some other pattern. The residual plot should not become much wider or thinner when viewed from left to right. This confirms the requirement that for the different fixed values of x, the distributions of the corresponding y values all have the same standard deviation. The chocolate Nobel data are used to obtain the accompanying stat disk generated residual plot. When the first sample x value of 4.5 is substituted into the regression equation of y hat equals negative 3.37 plus 2.49x, we get the predicted value of y hat equals 7.84. For the first x value of 4.5, the actual corresponding y value is 5.5. So the value of the residual is observed y minus predicted y equals y minus y hat equals 5.5 minus 7.84 equals negative 2.34. Using the x value of 4.5 and the residual of negative 2.34, we get the coordinates of the point 4.5, negative 2.34, which is one of the points in the residual plot below. See the three residual plots below. The leftmost residual plot suggests that the regression equation is a good model. The middle residual plot shows a distinct pattern, suggesting that the sample data do not follow a straight line pattern as required. The rightmost residual plot becomes thicker, which suggests that the requirement of equal standard deviations is violated.